Yeah, we were looking at, I think, Pythagoras Theorem in the last session. Actually, that was a wrong starting point, Because it is so popular, I thought I would start with that. Really, what is known as the first theorem of geometry is not Pythagoras Theorem. It is Thales Theorem. Thales. In fact, Thales is recognized as the first mathematicians in the history. Thales said, if you look at similar objects, similar means they look similar for us, but they are different sizes. Their corresponding sides are on the same ratio. That is all he observed. If you take a small cube and a bigger cube, each side is increased by the same factor, the corresponding sides. You should always look at corresponding sides. And the simplest example is a triangle. If you take two triangles, let me just draw those here. I have got one triangle ABC and I want to draw a similar looking triangle which is bigger than this. They are similar looking. From your eyes you can make out. That is because the three angles are equal. So that is the definition of similar triangles. When are the triangles similar? The three angles are equal to the three angles. So that means I have the side ABC, so I have got the angles ABC. You can call them vertex ABC is the same as angles ABC. And the corresponding triangle DEF, which got the angles D, E and F. Angle A is same as angle D, angle B is same as angle E, angle C is same as angle F. When that happens, the corresponding sides are in the same ratio. That means actually Thales theorem states that now AB and the corresponding side is DE. That means you have to take the side which is opposite the equal angles. So angle C I have taken, opposite that is the side AB. Same way angle C is equal to angle F. You have to take the opposite side which is DE. AB by DE equal to BC by EF equal to CA by FD. I can write this very easily even without looking at the diagrams, because I have written the triangle name itself. I can call this ABC, I can call it ACB, I can call it CAB, I can call it in any order of the vertices, right? But I prefer to call it in the order in which the angles are equal. That means when you say I've got a triangle ABC is similar to the other triangle, I'll write the vertices of this triangle in the same order of the angles that I have got. So we write that as similar to DEF. Then you can see the first two letters AB, first two letters EE. Second and third BC, EF, CA and FD. That becomes very simple to write. This way of writing symbols is actually called symmetry. We should write in a symmetrical way. Advantage is very easy to by heart. You are not likely to make a mistake also. So that is important. And we will see the importance of symmetry itself in some proofs slightly later on. I would like to show you as a separate example. Now, to prove Thales theorem, we have a problem because it requires a construction which is not the usual type of construction. Like I said, I am always worried about construction in geometric proofs. Here the construction is very peculiar. He says the objects are so far away from one another, it's very difficult to make any judgments or whatever, correct? So first thing that we need to do is physically you imagine You have to imagine only moving this second triangle that you have, moving it from here and placing it on top of the first triangle, so that the vertex D coincides with vertex A and the side DE coincides with the line AB, and since the angles A and D are same, we can expect that DF will definitely coincide with the line AC. So we just have to move it, and when you move it, what is the picture that we are likely to see is like this, right? So AB gets extended up to E, AC gets extended up to F, correct? So I'll read. So just visualize that now our triangle DEF is in the same place as ABC. This is the construction actually. First part of the construction is this. And since A and D angles are same, that is same, correct? Now we know that the angle B was originally given as equal to angle E, correct? Because they were similar. Now since I moved it here, that angle E is moved here. Therefore, this is equal to this angle E. And now you can see this angle ABC and angle AEF, they are equal. They are corresponding angles for these two lines. Just imagine BC and EF as two lines, and the line AE intersects those two lines. These two become corresponding angles which are equal. Therefore, BC and EF must be parallel. That is the first conclusion we draw is BC and EF are parallel. Whenever you have parallel lines, you can think about areas in a slightly different way. For example, supposing this is a separate diagram which only for visualization. Supposing I have two parallel lines. Okay. The first one I have written solid here, and we have a base here. Visualize two endpoints, we'll call it the base. Now I can place the vertex of a triangle anywhere on the other parallel line, correct? So that means I can have a triangle like this, or I can have a triangle like this, correct? All different shapes. But then if you look at the areas of these two triangles, base is common base is there, and height is the distance between these two parallel lines. And the minimum distance we know is the perpendicular distance. That is same for all triangles which are on with a vertex on the other parallel line. That means half base multiplied by height is same for any of those triangles. That means all these triangles have the same area. That's the conclusion that you have to draw. So wherever you find parallel lines and a base, you visualize the vertices on the other parallel line, and any triangle that you draw will have the same area, correct? No? So in this case, for example, I got BC and EF as two parallel lines, correct? Now if you want to get a triangle out of it, you need vertices, right? So the construction now, actual construction is join EC and BF, correct? Now if you assume BC as the base and E and F are two vertices which are on a parallel line, so the areas of, so that means now you can write that one statement, area of triangle BCE equals area of triangle BCF, correct? No? They are equal. BCE and BCF, they are on the same base BC and between the same two parallel lines. Height is same. Once you have this, now BCE, I got one more triangle here which is ABC, right? Supposing we add, so that is the next part of the mental construction or algebra is add area of triangle ABC here and also here, both left hand and right hand side. You add the area of triangle ABC so that we get a bigger triangle. So if you add ABC triangle to BCE, you get ACE, correct? So area of triangle ACE is same as that of triangle ABF. Correct? When you add ABC to BCF, you get ABF. So those two triangles have the same area. So that is one conclusion. Now the next step is to compare the areas of two triangles which have the same vertex. So that means, and different bases. So I can have one base here, I can have another base here, which are not necessarily equal, right? But then I've got a common vertex. No parallel line required here. So I draw two triangles from the same vertex to one base, same vertex to another base. Correct? Now the height of both of these triangles is the same because that is from the same vertex to the same line, horizontal distance. Height is same. Therefore, their areas are in the ratio of the base lengths. Correct? No? You understand? So that means now if you compare triangle ABC with AEC, that's what I am comparing. So area of triangle ABC divided by area of triangle AEC. ABC and AEC. Now the base of one is AB is one base, correct? Other base is AE. Part of that is AB only, but actual base is AE. So this ratio must be equal to AB divided by AC. Correct? Same way, we take the same triangle ABC, compare with the area of ABF. Correct? Area of triangle ABC divided by area of triangle ABF. Here AC and AF are the two bases and B is a common vertex. Therefore, the ratio will be AC by AF. Earlier, I think I wrote wrong, was AB by AE. Correct. Is that right? Now, we have also found that the area of triangle AEC and ABF, they are same. They are equal. We already found that. And the numerator is same. Therefore, these two ratios are actually same. Correct? So, which means AB by AE is equal to AC by AF. And we exchange the numerator denominator. We can say AB by AC must be equal to AE by AF. Correct? And AE, you can also write AE as D. Both are same. D and A are same points, right? And AF is same as DF. So AB by AC must be equal to DE by DF, which means the corresponding sides are in the same ratios. And we can move the triangle to a different vertex, you can prove the other ratio also is the same. The three ratios, corresponding side ratios are equal for both the triangles. Is that clear? Okay, now this Thales theorem, like I said, one of the first theorems. If you want to think of Pythagoras theorem as the second theorem, we can easily prove Pythagoras theorem using Thales theorem. That proof I would like to give you next. So as usual, we draw one rectangle triangle. Remember this, like I said, Thales theorem is more fundamental because it deals with any triangle, not necessarily right angle triangle, whereas Pythagoras theorem is specific to right angle triangles. So it is a specific. So let us say we have a right angle triangle. ABC. I've got the angle A as a right angle. Okay. Now here Pythagoras theorem states that the squares on the two sides, AB squared plus AC squared, they add up to square on the hypotenuse, which is BC squared. That is what we are supposed to prove. And the construction here is to get some similar triangles. See, once you get similar triangles, you can always apply Thales theorem. No? Is to drop one perpendicular from A to BC. This is the construction. We call it a point D. Now, how many triangles are there now in our diagram? There are 3 triangles actually. Not 2, there are 3 triangles. There was one triangle ABC, it is still there. I got a new triangle ABD, and I got one more triangle which is ADC. Now, do they look same shape or all different shapes? They look different shapes, no? Yeah, that is the problem with our human eye. Let me tell you, these 3 triangles are all similar. ABC is similar to ABD, which is similar to ADC. They don't look like it, but they are actually similar. Proof is very simple. I'll show you. How I did that was, I'll show you a demonstration for it. Now I want a right angle triangle of 2 different sides, not equal sides, is to take a rectangular sheet of paper and fold it on a diagonal. Correct? No? That's what I did. So now I got a right angle. I got a right angle triangle now of longer side, smaller side and hypotenuse. Correct? No? Now I have to drop a perpendicular from this point of right angle to the base. Correct? That I have done here. One more sheet of paper where what I have done is to drop this perpendicular. You can see, I don't know if you can see that. This is the perpendicular. Okay. So now I got all the 3 triangles here actually. When I fold it like this, I got a smaller triangle, right? This side, you can see, this is one triangle. And I got a bigger triangle here. You can see that, right? Other than this, you can see the bigger triangle. And the full size triangle is there, of course. That is also there, right? Now, to prove they are similar, the thing is, they are at different angles. That is why they don't look similar. You have to move these triangles around to match the angle, then you will see the similarity. That I will show you here. So I had the original triangle like this, right? ABC, correct? Now, we take this small triangle, for example. You have to match the 90-degree part and one part. Ignore this part. See that? You can see they are parallel. Similarly, if you want the bigger triangle, this piece, I can match that also. This is that bigger triangle, center, this bigger triangle, that you place it not like this, but like this. These 2 lines are parallel again. In fact, to prove that, it's very simple. Remember, angle A here in ABC is a right angle. Therefore, B and C are what are called complementary. They add up to 90 degrees. We have 190 degree there, total is 180, therefore B and C must add up to 90 degrees. 2 angles which add up to 90 degrees are called complementary. They complement each other to make up a 90 degrees. And 2 angles which add up to 180 degrees, they are called supplementary, because they add up to 180 degrees. They are called supplementary. So these two are complementary angles. Same way, in the triangle ABD, which is also a right angle triangle, D is the right angle there. Therefore, what is the complementary to B is this angle here. So, which must be equal to angle C. Correct? So, I will draw three lines there. So, when you drop the perpendicular, one side you get an angle which is same as angle C. Same way, the other side, this side is complementary to C, which is same as B. So, that will be equal to B. Two lines. So, now you can see each of these triangles. Triangle ABC had angle A, B and C. Triangle ABD also has got B 90 degrees and C. Same way the other triangle also. So, all three are similar triangles actually. So, now we can write the proof using Thales Theorem. I will show you that shortly. So, how do we prove that? We have to apply Thales Theorem. Like I said, symmetry is very important here, especially because the triangles actually look so dissimilar. Now, when we write the statement that these three triangles are similar, so we will say triangle ABC similar to, I don't want to write ABD because that's not the order of the angles which are equal. No? So, you have to write the letters ABD in the order of equal angles to ABC. A is the right angle, so you should write D first actually. Triangle D, next is B angle, and where is that B angle in ABD? The same B angle. B angle is the same, so we write DB and A. You have to write that as DBA. It is similar to DBA, not ABD. ABC is similar to DBA. Similarly, is also similar to the other part. Again, you have to start with D only because that is the right angle. D. Then angle B is above there, not here. You should not write DCA. You should write that as DAC. Correct. When you write this similarity like this, you have got three triangles which are similar. So I can compare the proportional sides of these two and these two or these two, whatever pairs of combinations that I can use, right? So I plan to use, see, our interest is not in AD. We are not interested in AD. We are only interested in AB, AC and BC, right, for Pythagoras Theorem. And because BC we are interested, so we will be interested in BD and DC also. But not AD. We are not interested in side AD at all in this discussion. So, we will say in the triangle ABC, I want to take one side which is AB. And the corresponding side in DBA will be the first two letters. DB equals, and the other side in ABC, or if you take DBA, would be interested in BD, or in the case of ABC would be BC. BC, next two letters is BA. Correct? These ratios are same. AB by DB is same as BC by BA. No. This is correct. Perfect. We do a cross multiplication, which means AB squared equals BC multiplied by DB. Correct? Same way, we now look at similarity of ABC with DS, the other triangle, not the center one. First and the last. And we say, in this case, obviously interest is AC in this case, not AB. Correct? AC divided by DC. First and last letters. right? And first and last letter, which is correct. AC by DC must be equal to BC. Second and last letter must be equal to AC. Right? Cross multiply. Therefore, AC square equals BC multiplied by DC. Simple. Add these two. Left hand side is AB square plus AC square. What is the right hand side? BC multiplied by DB plus DC, which is BC, is BC square. Pythagoras. Right? Simple. So this proof was given by Einstein. Einstein gave the proof nearly 2000 years later than the Euclid's proof, which we saw in the last session. Okay? But here now you can see how many mathematicians have been there in 2000 years. Right? It required an Einstein to realize that these three are actually similar triangles because they don't look similar at all. But once you have the similarity, you have to jump at it and say, I can apply Thales Theorem. Anywhere that you see similar triangles, apply Thales Theorem. That is the fundamental thing. Anywhere you see a right angle, think of applying Pythagoras Theorem because that is the natural consequence. Right? This is fine. Now, I would like to give you a third proof for Pythagoras Theorem, which contains huge amount of construction. It's like building a house actually, but the proof is less than this length. This itself is two-line proof, if you can think of. That would be a one-line proof for Pythagoras Theorem, but the construction is, like I said, huge construction. Right? I'd like to show that. Also as a just academic interest, not a big deal. We know that Pythagoras Theorem is true, everybody knows, but just to get you an idea of the amount of constructions that mathematicians visualize, not just drawing one perpendicular or one parallel line, they think of constructing many things when compared to the actual diagram which is there, right? So we start with this same. We start with one right angle triangle. This is a 90 degrees written as a, not an arc, but a square. Now, I have written that in black. Now, I will do all the construction in blue, right? Main constructions. And there is one sub-construction also. I will do that in red. Like I said, this is going to consist of mainly constructions. This is the entire proof. First step is, we'll give names for the sides actually. So, you can call the triangle ABC, of course, no questions. But what are the sides going to be? Opposite vertex A is the side A. Opposite to vertex B, opposite to vertex C, right? A, B, C. So I got, now I have to actually prove C squared is equal to A squared plus B squared. That is what I'm supposed to prove. So now construction is, you stretch this line further and equal to the distance the other side. So I got a side B here. We stretch the same line with an additional distance of A. There we drop a perpendicular. Draw a perpendicular whose length is B again. AB. Now we join this hypotenuse. Okay. So now I got two triangles which are not just, of course, these two are similar. I have not quite drawn the correct sizes, I think. That's why they don't look congruent. They're actually congruent. Okay, because the three sides, I got a right angle, right? And I got these angles actually. This angle, if you look at these two angles, they are complementary because adding another, sorry, this is not a 90 degree, no? This is a 90 degree. I've got a 90 degree here, right? Common. And side B and side B is common. Side A and side A is common. So that means I got two sides and included angle, they are same, correct? So when you have a triangle and I got two sides and the included angle same for another triangle, they are congruent. They are same, identical. Congruent means identical. So the third side also is equal, other angles are also equal. Two sides and the included angle you have to see. Okay. Similarly, one side and two angles on the two sides, two parts of that side. That is, I got one side and I got one angle, another angle. Same way, I got the same length side and the same angles. When you draw, you get identical triangles, right? And the two angles, because two angles are same, third angle also is same. No questions on that. They are similar and they are also congruent because the two sides are same. Just because one side is same and three angles are same, not necessarily they are congruent. That means, for example, take one isosceles triangle. So ABC is an isosceles triangle and I stretch this to D and draw another side AD. Now, if you look at the two triangles ADB and ADC, this angle is same and this angle is same. No. If you look at triangles ADB and triangle ADC, right? Angle D is common for both. Angle C also is common for both. Two angles are same, so the third angle also must be the same. And one side is same, AB and AC are same, but they are not actually congruent. They are different, they are only similar. So you should be careful when you look at congruence. So now in this case, these two are congruent because two sides and included angle are same, right? So they are congruent. Therefore, the third side also must be same, which means this is actually C, right? And now you can see the two angles here. If you want, I'll write the names of vertices. I got one A, B, C. A is stretched to D and E. Right. So if you look at angle CAB and CBA, they are complementary because of the 90 degrees, correct? Anyway, since
angle B and angle E are
no. Anyway, angle CAB and angle CAED, they must be same because they are actually congruent triangles. They are congruent triangles. They are equal. Right? Which means, since these two angles here, angle A and B are complementary, the corresponding angles here, E and A, also must be complementary, 90 degrees, and the balance angle must be 90 degrees. Therefore, we conclude that this is actually a right angle. And that means, actually now you can see I had a hypotenuse C at 90 degrees. I have drawn one more side which is C, which means actually I have drawn two parts of a square. Two sides of a square I have drawn actually by this construction. We continue the construction and add one more side A and one more side B. We will get one more side C and also one more right angle. So we get a third side of the square, right? And last, we continue this construction and one more A and one more B and join. We get the fourth. Correct. By adding four identical triangles, adding three more identical triangles, what we get inside is the square of C, really. Now I got two squares here. One is the inside square and one is a bigger square. Bigger fellow also is a square because the side is A plus B, A plus B, A plus B, A plus B everywhere. So I got two squares here. Now how do I calculate the area of the big square? I can write a couple of names here. The E, F, G and H. So we are looking at the square CDFH. I want to calculate the area of that. One way is area of that is equal to area of square ABGE plus 4 times area of triangle ABC. Because 4 congruent triangles, all are equal area. So add the 4 areas of the 4 triangles, add to the area of the inner square, I get the area of the outer square. So that is one way of computing.
CDFH. A square.
AB,
First one.
this one.
CDFH. CDFH. You had written.
CDFH. Correct. CDFH. Right. Now there is another way of computing the area of the big square is to complete the inner squares. That means what we do here, we draw intermediate line at the distance B. And intermediate line at a distance A. That means actually what I have now done is to split the big square into one square with a side A in one corner, square with a side B in another corner, and 2 rectangles. Both rectangles are A and B, A and B. Correct? So therefore, area of the same square CDFH will be area of, I will write simply as A squared. A square plus B squared plus 2 times the rectangle, right? Which is 2 times AB. Both are same. So now, triangle ABC area, half base into height because it is a right angle, is half AB. I can change this value to half AB multiplied by 4 is 2AB. So therefore, what is the area of ABGE? Is A square plus B square. Pythagoras Theorem. So much of original triangle was there. You see the amount of construction which was made, but the proof is only 1.5 lines. Anyway, that is besides the point. I would like to proceed beyond this point to look at properties of triangles, I think is what I am really interested in. Now, when you say I got a triangle, we've got 3 vertices, 3 sides, 3 angles, right? So now we would like to introduce many more lines using these three sides and find if there are any special properties of a triangle which are useful in computations. The first such is what is known as an orthogonal bisector. Orthogonal bisector, when you say you got a line, call it AB. A and B are called the end points of the line. There are 2 points. I have joined them to get a side AB. Now, what is the orthogonal bisector of this line? Bisector is cuts it into 2. Orthogonal is at right angles. So, I want to draw a line which cuts this line into 2 parts exactly at the center, but in a vertical direction. That means at 90 degrees. Right. So, what is the property of this orthogonal bisector? Is as follows. You can take any point on the orthogonal bisector, call it P. We can prove that it is equidistant from the 2 endpoints, PA equal to PB. Regardless of which point you choose on the orthogonal bisector, it's always at the same distance from A and B. And how to prove that? Is a very small construction can prove that. Is you join this, you want to get a triangle, so join AP and join PB. So now I got 2 triangles, we can call this point D. PD is the perpendicular bisector of AB. So I got 2 triangles, APD and DPB, which now you can see these 2 sides are same because it is a bisector. AD equal to DB. These 2 sides are same, right? We show that by drawing one line here and one line here, saying they are same, right? And the side PD is actually common to both the triangles. So that is same, right? Second. And because of Pythagoras theorem, hypotenuses are also same. So this also is equal to that. So they are identical triangles. Since hypotenuses are same, P equal to PB. Now this is true for any point on the orthogonal bisector. And the converse also is true. That means if you have a line AB and you have a point P somewhere, doesn't matter where, which happens to be equidistant from A and B. That means PA equal to PB, then P will be on the orthogonal bisector of AB. You can prove that also by the same Pythagoras theorem. You can simply prove the converse of this also as a proof. Now, if you take a triangle, how many orthogonal bisectors we can have? We can have 3 orthogonal bisectors because we have 3 sides of the triangle, correct? Got a triangle ABC and we can draw the 3 orthogonal bisectors. I will draw only 2 for the moment. I will not draw the third one. That means we have triangle ABC. I have drawn the orthogonal bisector of BC and AB. They intersect at a point because they are not parallel, definitely. And I am calling it G. Okay, I am calling it G. Whatever intersecting point. Now G is on the orthogonal bisector of BC, therefore it must be equidistant from B and C, correct? So GB must be equal to GC, no questions on that. G also happens to be on the orthogonal bisector of AB, therefore GB is also equal to GA. Correct? So now we have GA equal to GB equal to GC. In other words, I have GA is equal to GC. Remember, we got G without any reference to AC. But we find that I got a point G which is equidistant from A and C. Therefore, G must be a point on the orthogonal bisector of AC also. Right? That is the proof for the theorem which says orthogonal bisectors of a triangle are concurrent. Correct? I shouldn't have called it G, I should have called it O or something, but doesn't matter. What is in a name. It's okay. So the three orthogonal bisectors are concurrent. They pass through the same point. That is a special property for any three lines. Any three lines, if you take, concurrency is a special property of any three lines, and these three lines happen to have that particular property. This is for orthogonal bisectors. Okay, fine. So we take the next set of lines, which are properties of triangles, with the angular bisectors. We have three angles, therefore we can have three angular bisectors, and we'd like to prove that they are also concurrent. Now, what is an angular bisector? You have any angle, and we bisect the angle exactly in half and draw a third line. Now, the property that comes is, supposing I've got this, you can give some names to these. I got A, B, and C, right? So I got the angle ABC, the two sides BC and AB, and I'm bisecting the angle ABC so that these two angles are same. Correct? Now, the property of this bisector is, take any point on the bisector, call it P. Now, P is equidistant from the two sides. AB and BC. Now, what is equidistant from a line? What is the distance of a point from a line? Is the perpendicular distance. That is the least distance. No? That's what we call distance. Distance from BC to P, I can have a line, I can draw anywhere. No? But we are actually talking of the perpendicular distance. That is called the distance. From a point to a line, distance is perpendicular distance. Now, that is. Now, the theorem or lemma is, any point on the angular bisector, it is at the same distance, perpendicular distance from the two lines. So we can give a couple of names, or you can call this itself is point A if you want, or I can give a name to this. You can call it D, and we can call it E. Right. So I drop the two perpendiculars, PD and PE. We have to prove that PD equal to P, correct? How do we do that? Same. Use congruence of triangles. Now I got two triangles, BPE and BBD. I got two triangles in which one angle 90 degree, another angle 90 degree. One angle is same. Now this angle PBE is same as BDBP because we have the bisector. Now, because the bisector, these two angles are same. If two angles are same, third angle also will be definitely the same. No questions on it. So they are similar triangles. In addition, they have a common side which is BP, which is opposite the 90 degrees. No? There is a corresponding side. Actually, it is a corresponding side which is same for both. Therefore, they are congruent. These two triangles are congruent. That means all sides are equal. Therefore, PE, which is opposite the angle PBE, must be the same as PD, which is opposite the angle, equal angle PBD. So, PD equal to PE is the conclusion. And the converse of this also is true, lemma, which means I got two lines and any point in between, right? So, what is the converse of this? I can take a point. If that point happens to be at the same distance from the two lines, it must be on the angular bisector. Proof is same, very similar. Same by proving them as congruent triangles. You can do the same proof, no problem there, right? So now we make use of that property of angular bisectors to prove that they are concurrent, correct? That's a two-line proof again. So as usual, I have a triangle ABC. We draw only two bisectors. Maybe bisector of angle B and bisector of angle C. And they intersect at a point. This time I like to call the point as I. I is a point, name I would like to give, right? Now, this theorem tells us that I is equidistant from, on the angular bisector of angle ABC, it is equidistant from BC and AB, correct? It is equidistant. Now, I also happens to be a point on the angular bisector of angle C here, therefore it is equidistant from BC and AC, which means you combine the two results. Therefore, I is equidistant from AB and AC. Therefore, it must be on the angular bisector of angle A. Correct? Therefore, the three angular bisectors are concurrent. And if you drop the three perpendiculars, all the three perpendiculars have the same diameter. And you can actually draw a same distance. All the three perpendiculars are the same distance. So actually we can draw a circle through those points. This circle is known as incircle, because the circle is inscribed inside the triangle. It's just touching all the three sides. Touching means intersecting at only one point is called touching, just touch. But normal intersection will be 2 points, right? Or 0 points. In this case, a single point intersection is known as touching. No? Also say it is tangential. That means the three sides, all the three sides are tangential to the circle. No? Also you can think of it like that. So that is, now I have introduced the topic of circles before discussing what is a circle. I think we should have done that first. But let me finish this proof first, then we'll take up circle and proceed with triangles further, right? So now, this is known as incircle, right? Incircle. Now, when you say angular bisector, when you say I got an angle ABC, there are actually two angles. You just have to produce this side AB. If you produce it beyond B, I get one more angle. So I could have drawn a bisector of that angle also. This is a different bisector, angular bisector, which will be exactly orthogonal to this bisector, if you can figure it out, correct? Similarly, for C also I can draw one more bisector, which is bisector of the external angle, right? And they intersect at a point. No? I'll call it E. Now this point E, which is the intersection of the bisectors of external angles of B and C, right, is equidistant from AB and AC and BC again, same, correct? Therefore, I can draw one circle from here with those distances as radius. I'll attempt to draw a circle which touches all the three sides, right? I'll not complete it. And E will also be in the same line as the internal bisector of A. So, if one internal bisector and two external bisectors, they are concurrent, and through that as a center we can draw one circle which touches all these three sides. That is one side and the two extended sides it will touch, and that circle is known as an excircle. and that center is known as X center, whereas I was in center. Now remember, there are actually 3 X circles, not one. If you want to take internal bisector of B, external bisectors of A and C, you will get one external circle this side and then another X center. Similarly, if you take the internal bisector of C and external bisectors of A and B, you get a third X circle. So there are 3 X circles and 1 in circle, correct? And all those bisectors are concurrent. So that is a beautiful property of triangle. Now circle we should discuss, but there are 2 more interesting properties of triangles which I will discuss before we go on to circle. Let us assume that we understand what is a circle with the radius and so on. I have not yet discussed those aspects. Properties of circle, really we have not discussed. I would like to do that later stage, okay? Shortly later on. So is this clear in circle and X circle? So fantastic. So now we got 2 sets of, actually 4 here plus 1 more set. So 5 sets of concurrent sets of 3 lines each, correct? Now the other 2, these 2 are very simple to prove. Concurrency of angular bisectors or concurrency of orthogonal bisectors of sides was very simple to prove with a simple construction, right? Now the other 2 require peculiar thinking, peculiar construction, so we can take that up. One is medians. Three medians of a triangle are concurrent, okay? What is a median? Median is a line which joins one vertex of a triangle to the midpoint of the opposite side. It is known as a median. So I got a triangle ABC. Midpoint of BC is the point D, and a line joining A and D is known as a median. That's a median. I can draw one more median from B, right, which joins midpoint of B to AC, correct? Call it E. They intersect at a point as usual, and that point actually is called G. I gave a wrong name last time, doesn't matter. G, right? C also has got a median. We have to prove that the median through C also passes through the same point. G is what we are supposed to prove, saying all the medians are concurrent, right? And what is the construction for this? Construction is a bit peculiar, but you have to probably by heart it. Is from E, draw a line which is parallel to the median AD. See, as soon as you draw a parallel line, you get lots of similar triangles, because you got corresponding angles which are equal, so you'll start getting similar triangles. So I'll call this point F. Correct? Now, if you look at the triangles CEF and CAD, they are similar because I got 2 parallel lines, one single vertex, you got a corresponding angles which are equal. I won't even mention that. So, triangle CEF is similar to triangle CAD. I have written the vertices in the correct order. Angle C same, angle E will be equal to angle A, and angle F will be equal to, angle, yeah, correct.
Angle D. angle E.
Is right. It's correct. The same. Which means the sides are proportional, right? So what are the sides I am interested in? Here is CE divided by CF. Should be same as CA divided by CD. Correct? Now we exchange this denominator numerator. No? I can relate the same thing as this implies CE by CA equals CF by CD. So CE by CA, what is the value of CE by CA? Remember, BE was a median. Therefore, E is the midpoint of AC, that is known. Therefore, CE by CA is equal to half. So, CF by CD also must be equal to half. So, if CF by CD is half, that means CF must be equal to DF. Correct, no? Very equal. Now, on top of that, we have D, which is the midpoint of CB. Correct? Therefore, each of them will be equal to 1/4 of BC. BC, half of BC is CD, half of that is DF. Correct? Now we look at, you can say 1/4 of BC, or you can say DF is half of BD. It also is the same statement. Now we look at two more similar triangles, same two parallel lines with a B as the vertex. So what are the two triangles? I got one triangle BGD, which is similar to triangle BEF. Correct? BGD is similar to BEF because you got two corresponding angles which are equal and angle B which is equal, so they are similar, right? So once you have similar, we write the same ratios. So what is BG divided by BE corresponding? BG divided by BE equal to BD, that is the first and last letters, must be equal to BF. And what is BD by BF? We got here is 2. BD was twice BDF. Therefore, BG must be twice GE. Correct, no? So, which means now I have two medians which had intersected at a point G. We also happen to know that G is 2/3 of the way on the median. From B, it is 2/3 of the way because BG is twice G, 2/3 of the way, right? Now, this 2/3 of the way I could have proven by symmetry. Instead of using the median from A, I could have used median from C also. That also would have intersected the median BE at a point which would be 2/3 of the way now because the proof is similar. Which means C's median must pass through the same point G because it is 2/3 of the way from the vertex. Therefore, they are concurrent. The proof is clear, no? Only two lines, but then that is the logic. Logic is, I take two medians and I find that it is 2/3 of the way they are intersecting. Any two medians I take. So I take these two medians, 2/3 of the way. Other median also would be 2/3 of the way. That means that other median also must be passing through the same 2/3 point, which is what we call G. Right? Now on medians there is one more construction that people make. I'll show you that as a separate diagram. I don't want to confuse this picture, because for proving medians are concurrent, this is the construction that you have to remember. That one line that we draw as parallel line, right? Write two medians and draw one parallel line. That is all. That is the construction. Now I'll draw a separate triangle here and draw all the three medians. So I got a triangle ABC. I've drawn the three medians AD, BE and CF. And their common intersecting point, we call it G. We'll continue to call it G, correct? Now how many triangles we have now? We have one big triangle ABC, of course, and we have 6 small triangles actually, right? 6 small triangles. I want to prove that all 6 have the same area, which is 1/6 of the total triangle size. Okay. How do we prove that? It's extremely simple. It's the same base and common vertex for area of a triangle that we use, the same principle that we are going to use. So I'll show you the triangle that we are going to compare. One is, first is we take triangle ABD and triangle ADC. Their height is same because vertex is common and the baseline is common, so height is the same. And the base are equal because that's the midpoint, they are equal. Therefore, they are the same area, correct? No questions on that. In these two triangles, big triangles, I will take a sub-triangle which is from point G. Same logic. I got the two bases which are equal and a common vertex, which means height is the same. So these two triangles GBD and GDC are of the same area. Now you deduct the area of GBD from ABD, deduct the area of GDC from ADC. What are you left with? AGB. So we are left with the triangle AGB on this side, and this side we are left with triangle ACG or AGC, correct? AGB and AGC are equal. They are same area, correct? By the same logic, by symmetry, we can also say triangle BGC also will be the same. That means triangle GAB, GBC and GCA all are same. All are three equal areas. We have proved that, which means each is 1/3 of the area of the triangle itself. These two are also equal, these two are also equal, which means all the 6 are equal. And they are all 1/6 of the total area of triangle. That's why the center point is the center of mass for the triangle itself, called centroid. The name is centroid. G is called centroid because it is the center of mass. Center of gravitational mass, which means if you stick a pin here and lift the triangle, it will exactly balance. It can balance. It's got the area spread all directions equal. So that's why it's known as centroid. Okay. Next we go to the next, after medians, orthogonal bisectors and angular bisectors, we go to the fourth type of lines, which are altitudes of the triangle. Altitudes of the triangle, right? So what is an altitude? So you got a triangle ABC. Altitude is the perpendicular from the vertex to the base. It is known as an altitude. So from A, for example, I have dropped the altitude AD. Same way, I can drop an altitude from B onto AC, which is a perpendicular from B to AC. I can drop an altitude from C to AB, which is a perpendicular from C to AB, correct? So I got 3 altitudes. We would like to prove that they are also concurrent, which would be a tremendous thing for triangles, right? Everything concurrent. Very nice. Now this, unfortunately, for us, I discovered requires a construction. I don't know how Euclid came up or some other mathematician came up with that construction. Something like that Pythagorean area that we constructed was too complicated, but somehow they visualized that picture. This picture, I can't even visualize that construction that they did. And the proof is half line again for that. For proving concurrence of altitudes, proof is only half line here. I don't even have to write down the proof. It is self-evident, but it's all in the construction. And how they came up with that construction is something I have absolutely no idea at all, which also means one more thing. In fact, that is what I want to discuss next. That's why I took this up as the last example in our discussion of triangles before you go to circles. Because that is the way you have to think if you want to become some original thinker. No? See, there are original thinkers and non-original thinkers. The original thinkers always come up with some ideas which nobody else has come up. Like one example I already gave you. Einstein came up with the idea of proving the Pythagoras Theorem using similar triangles. For 2000 years, don't tell me, there have been thousands and thousands of mathematicians who have looked at Pythagoras Theorem. Thousands of proofs have been given actually. There are thousands of proofs for Pythagoras Theorem. But it required an Einstein to provide that next fantastic proof for that Pythagoras Theorem after 2000 years. So, no, I'm saying that's the type of deep thinking that you have to employ in every subject, as an example. So, what is the construction here? God help us with this construction, but I will go ahead and do it anyway, right? But it also requires one lemma which perhaps I can state to start with, is a parallelogram. Everybody knows what is a parallelogram, right? Parallelogram is a quadrilateral which is the result of 2 pairs of intersecting parallel lines. So, I got one pair of parallel lines intersecting with another pair of parallel lines. Right? Those 4 intersection points form what is known as a parallelogram. Right? Now, this parallelogram, one property of parallelogram is opposite angles are equal, one thing. Because of corresponding angle which is an alternating angle, so opposite angles are equal, no questions on that. Second most important property is opposite sides are also equal, correct? I mean, how do you prove that? Very simple, drop one perpendicular and then using Pythagoras theorem you can very easily prove that parallelograms have opposite sides which are equal. No questions on that. You can take it as an axiom or you can prove it also, no problem. So now coming back here, now I want to get n number of parallelograms. Actually in this picture, I've got only a triangle. Now I have to get lots and lots of parallelograms, is to draw lots and lots of parallel lines basically. That's what you have to do. So through A, vertex A, we draw a line which is parallel to BC. Through vertex B, we draw a line which is parallel to AC. Through C, we draw a line which is parallel to AB, obviously. So now I have drawn 3 lines now, which of course are going to form a triangle, right? It's a bigger triangle, much bigger triangle than ABC. I got a new triangle. We can call it, as usual, you can call it D, E and F. Right? Now, where are our parallelograms?
ABC.
Okay, let's look at one example. Let me show here. One is this itself. This is a parallelogram. Of course, we should also get a matching parallelogram for doing any theorem proving. I got one parallelogram which is AFBC. I got one more parallelogram which is ABC, correct? So now you can see I got two parallelograms based on BC, one which goes to AE, other which goes to AF, correct now? Two parallelograms. And in each of these parallelograms, opposite sides are equal, we know that. Therefore, BC's opposite side is AE, AE must be equal to BC. No questions on that. Same way, in this parallelogram, BC must be equal to AF, no questions on that. Now you can see BC is equal to AE as well as BC is equal to AF. Therefore, AE must be equal to AF. So, A is the center point of FE is the conclusion, right? By symmetry, or you can draw other parallelograms or compare other parallelograms, you will find that B must be a center point of FD, C must be a center point of ED. No questions. Therefore, what is the conclusion? The altitude that we drew for triangle ABC from vertex A is actually the orthogonal bisector of side FE in the triangle DEF. Correct? That altitude is same as the orthogonal bisector because it bisects the side and it is 90 degrees. Correct? So therefore, the three altitudes of triangle ABC are identical to the three orthogonal bisectors of triangle DEF, which we have already proved are concurrent. Therefore, altitudes are concurrent. I won't even write those statements, right? It's just logic. No need to write any something equal to something is not required, right? Everything is just pure English words which proves the theorem that altitudes of a triangle are concurrent because they happen to be orthogonal bisectors of a much bigger triangle, which we constructed. As I said here, the construction is the proof because that somebody has visualized this construction where the altitudes happen to become the orthogonal bisectors of another triangle. Therefore, for any triangle this is true, therefore they are concurrent. Correct? Fine. So we leave the triangle there for the moment. Now we go on to circles. Circle also was one of the important shapes which the Greek mathematicians and Indian mathematicians studied as important as triangle. No? In fact, triangles and circles make up most of the geometry topics that we think of. Now, what is a circle? Circle is very simple. You got something called a center, which is just any point that you want, and we draw the locus of another point which is always at the same distance from that center, no? Equal distance from the center is known as a circle. It's known as a circle. Now I can draw different circles with the same center. No? They are actually called concentric circles. No? Like concurrent lines, I can have two circles which are concentric. That means the center is the same for the two circles. One of the important measurements in geometry, earth measurement. One of the important things in earth measurement was to measure the length of the circle itself was an important aspect. So how do we do that? It is very simple. Supposing I draw two lines which are two radii, which is known as a radius, right? Two radius. Now these radius can be far off. Actually, we have the two arcs here. Actually, we have two arcs here. But I can join these two by a chord also, which is slightly inside. Correct. For the two circles I have drawn. So once you draw that, now I got two triangles here. I got a small triangle. The chord, this is known as a chord. No? Any line which joins two points on a circle is known as a chord. That's a chord. So I got a chord here, and these two sides which are radii equal actually. Similarly, I got a chord here and I got two sides which are radii which are equal again. So I got actually two isosceles triangles. Isosceles is two equal sides. Two sides are equal. Two isosceles triangles with common angle, which means they are similar also. They are similar. You can see they are similar, no? Because this inside angle is same. Isosceles has equal angles, and since the three angles have to add to 180 degrees, so obviously the other two angles also must be same. Or in fact, the cards are parallel, so corresponding angles are same, whichever way you want to look at. So they are similar triangles, right? They are similar triangles, which means the sides are proportional, which means if you look at the length of a card, take a card, length of the card is the same ratio as, is proportional to radius. Correct, no? Length of the card is proportional to radius. That means the longer the radius, if you double the radius, the card length also will get doubled. No? That's the meaning of that proportionality from Thales Theorem. I am just applying Thales Theorem here for these two triangles. The length of the card is proportional to radius. Now what we do is, we reduce this length of the card by bringing the second point, radius, closer and closer to the first point. If you keep reducing it, you will find the card will merge into that arc itself. No? Correct? No? It will almost become the arc. No? Infinitesimally, if you see, I can reduce it as much as I want. So if I reduce this angle, what I am saying is, we can keep reducing this angle, keep squeezing it, then the card becomes closer and closer to that arc, right? So eventually you can say when it is very small, I will assume card length is same as arc length. Correct. So that means we can also say, and since it is always proportional, we can make it as an axiom saying length of arc is proportional to radius. Actually, it is length of the card, but I can say length of the arc is proportional to radius. Correct? So, in fact, if you keep going longer also, it will be proportional. So, any length of arc that you take will be proportional to the radius. So, that gives us a measure for the angle itself. Now, what is this angle? If I take the radius of a circle as 1 unit, length of the arc itself is treated as the angle. And they found by actual measurement, walk in a circle and measure the perimeter of the circle versus the radius. They measured it and found that this total arc length of the circle, that is the circumference, divided by diameter. Diameter is twice the radius. It is always fixed regardless of whichever circle that you write. Length of the circumference divided by the diameter is always a fixed value, and that is denoted by the symbol pi. Pi, I think it's called pi probably because, of course, pi is a Greek letter, I know. Probably because the name of Pythagoras starts with pi. Original fellow, no? So, pi. So that is known as pi. Right? So next step is, so that means the circumference is 2 pi r or pi d, whichever way you want to write it. Next step is to find area of a circle. By area of a circle, I can think of area of a sector of a circle, not the full circle, a part of a circle, which is known as a sector. Actually, what I have drawn here is a sector. Now, how do you find the area of a sector? Is the next step. This again requires a construction in geometry, which is, like I said, it requires some brilliant thinking to come up with such constructions, but then proofs are very simple beyond that construction. So what I want to do is I want to take an arc of a circle, and I want to find the area of this arc. Sorry, area of this sector. So this inside area, this area is what I am trying to find. Okay. There's a peculiar shape there because we got the two sides which are equal radius, and the third side is an arc, not a straight line. It's an arc. And we wish to find the area of this triangle. How do you find the area of this triangle? Construction is, area of the sector. How do you find that? Construction is as follows. First we divide the sector into two pieces by drawing a central bisector. When you write a bisector of this angle, now I got two sectors, both are equal in area, obviously, because length of the arc depends, ratio is only to the angle, no? So both angles are same, so lengths of arcs are same, therefore they are identical sectors, their areas are equal, right? Or we bisect again, no? Once again, we bisect these two angles. Now I got four sectors, all are equal area, correct? I can divide that once again, I will get 8 sectors. Now I am reducing this arc length so that we can do some infinitesimal calculation. And how do we do that calculation also is the next part of the construction is not to look at it as it appears there. Just assume that I have drawn 4 more, 3 more bisectors or whatever, so that I get 8 pieces. Assume that I got 8 pieces there instead of 4 pieces. I don't want to clutter up that picture. So now what we do is, we take the first such sector and place it vertically. That means I've got the arc and the two sides. Same sector, I'm putting it like this. Vertically I placed it. Okay? The first sector. Next sector, also I will take it, put the same way, but upside down. That means the arc will come on the opposite side. Correct? Third one, I will put it downside up. Fourth one, I will keep it upside down. Fifth one, sixth one, seventh one, eighth one. So those 8 sectors, I have placed them flat on a paper where I got the arcs, the total arc length, actually half of the arc is on the top and half of the arc is at the bottom and the side is the radius. Correct? Side is radius at an angle, of course. Now supposing we increase this number of pieces indefinitely, that means I add more and more, I create more and more pieces which are smaller and smaller and smaller. That means this radii also will become as right angle as possible. Now you understand, it will become vertical and the arc will become actually a piece of line. No? It becomes a straight line. So it becomes straight line. Correct? So eventually, if you make infinite number of pieces, for example, what I am going to get is a rectangle. Correct? Rectangle. And what is the height of this rectangle? Is radius. And what is the width or length of this rectangle? Is half the arc length. Because both sides is half, no? So half the arc length. And you multiply these two, you will get the area of the area of the rectangle, which will be the same as the area of the sector, correct? So half arc length, half radius multiplied by arc length. But what is the arc length itself? If you look at it as an angle, remember, arc length of a unit radius, arc length of a unit radius circle is itself defined as the angle. No? Angle, I will call it theta. Theta. What is the angle? Is the arc length of a circle of unit radius. That is defined as theta. Theta called radians. That is known as a radian. Radian measurement for angle. We were using degrees so far. Degrees is unable to write on paper saying 90 degree, 180 degrees and so on. But then if you want to use in calculations, we have to represent as a number. Degree is not a good for that purpose, so they use radians. And what is the radians? Radian measure is the angle of angle is actually arc length of a unit radius circle. That is known as that. And if you have any other radius, of course, we'll have a correspondingly bigger arc length. So what is the arc length of a circle of radius r? Radius is r, no? Is r theta. Because that has to be proportional, no? This is theta, this arc length is theta, and that is r theta. Because it's proportional to the radius. Correct? So therefore, what is the area of the sector? Half radius multiplied by arc length, which is r theta, which is half r squared theta. Half r squared theta is the area of a sector. Now, I want the full area, supposing I want the full area of the circle, and what is the angle, full angle of the circle is, how much is that? 2 pi radians. So 2 pi multiplied by half r square is pi r square. Therefore, pi r square becomes area of the circle. Okay. Pi is that universal number which is a ratio of circumference to diameter of any circle. So pi r square becomes the area of circle. Is that clear? Okay. Now, I was talking of a side topic about constructions, I think, because construction, once you do the right construction, proof becomes very simple. You have seen that, right? We saw it in the case of medians, we saw it especially in the case of altitudes, and we also saw in the case of Pythagoras Theorem, that if you come up with the right construction, the proof is going to be stupidly simple. It's obvious, you know. Now, how do we come up with such constructions? What is the thought process to go into those is a question. Our brain has to work overtime, no, to come up with those constructions on our own. These are constructions which some other mathematician has already made, and I have told you, now you know it. No? So, it's like a trick. Yeah? Basically, a construction is a trick. A trick is very difficult till you know it. Once you know it, it is stupidly simple. You know, that is the meaning of a trick. Same construction has got the same principle that it is like a trick. No? Now the problem is how do we come up with our own constructions? That how do you come up with your own construction tomorrow is the question, right? Now on that aspect, there are two things I can do. I can discuss a couple of puzzles with you, which I'll ask you to solve at home. Take your time, no problem. Do whatever thinking that you want to do, you do the thinking and come up with an answer for that. That is one issue. Second is, I want to look at that symmetry also in a bit of more detail to show you how symmetry can solve some of the problems which are otherwise a bit more difficult to solve. No? We did use the symmetry to look at a couple of issues, but I would like to look at a bit more detail on the symmetry, because many things become simple after you represent them using symmetry. So I would like to do that also. So let us look at the puzzles first, I think, which is a way of thinking only. This has nothing to do with geometry or even algebra or arithmetic. It's got to do only with thinking. So, there are two puzzles which I want to talk to you about. I might have discussed this with some of you earlier, but please excuse me if it is a repetition. Okay. Now, the first puzzle is on a box of balls. Tennis balls or whatever. You bought a box of balls, right? Now, when you buy one box, for example, 1A is I got 9 tennis balls. they are manufactured to be of some standard sizes and weights and measures, right? Standard mass. So all the 9 are supposed to be the same weight, of course, no questions on that. But unfortunately, what we got is a defective, manufacturing defect. So we got a defective ball. We got a ball which is slightly heavier than the others. Out of the 9 balls, 8 are very good, perfect, no problem, they are standard balls. But one ball is heavier. Now we got these 9 balls, how do we identify that one particular ball is the question. No? So we have to be able to separate it from the others. How to identify? One method which is suggested, I will give you the answer to this. I will give you the next level problem which you are supposed to think of, right? This I am giving you the answer to at least to start you thinking in the right direction at least, you know. So now I got a 9 balls. What the first thing that we do is separate it into 3 groups, each containing 3 balls. We can call them group A, group B and group C, correct? I got 3 groups, A, B, C. Each has got 3 balls, right? So now we take a balance, right? Actual balance, no? They use balance. I know you've seen, no? Nowadays they have electronic weighing machine, but this balance you would have seen, no? Physical balance. And I put group A balls into one side, group B balls into one side, the other side, right? A and B. We compare the weights. Now, if A and B contain all standard weight balls only, what will be the result? They will be the same weight, equal weight. So, possibility is, there are 3 possible answers when you weigh it, that group A total weight, no, is equal to group B is one possibility. Other possibility is group A is heavier than group B. Or third possibility is group A is lighter than, there is no light ball here. What we mean is group B is heavier than group A. Either group A contains the heavy ball or group B contains the heavy ball, or both contain, neither of them contains the heavy ball, right? Both contain standard balls, group A equal to group B. Now the defective ball can only be from one of 3, no? So what we do next is, we take one each of group C and weigh it. If they are equal, the third ball must be heavier. If they are not equal, whichever is heavier, of course, no question. In the case of not equal group A, group B also, we take the heavy side. It could be the group A contains the heavy ball or group B contains the heavy ball, which you got 3 balls, and take Y one against one, leaving out the third one. Now whichever is heavier, if one of them is heavier, If both are equal, the third one will be heavier, is the answer, correct? Now, what you have to do is, your problem is very simple, is 1B. Problem statement, I got 12 tennis balls. Same issue, one ball is defective, manufacturing defect, but the catch now is, it could be one ball is either heavier or lighter, I don't know, than the others. In 3 weights, now that one we solved in 2 weights only. Here you are given 3 weighings. In 3 weighings, you have to identify the defective ball and also tell whether it is heavier or lighter in all cases. Okay, that is your problem. You have to think. One more puzzle we'll come up with shortly after the break.